So in this video, we'll talk about how to use continued fractions to do the order finding. And this will be the final video on the order finding. The final piece of the puzzle of order finding is when we get the approximation of S over R, how do we get to the period R? And the key idea is this idea of continued fractions. So let me just remind you what the um, circuit looks like for the order finding. So we have the top register, let's say with T bits, T yet to be determined. Then we have the Hadamard tensor T. On the bottom, we have get 1. And then we have this control U gates, but then we saw that this is actually equivalent to this modular exponentiation. So this is x to the j mod n. And so this will create some j over here, this uniform superposition. And then finally, we have this inverse of the Fourier transform over here, and then a measurement. So that's the schematic of the order finding. And at the end of the measurement, we will get over here an approximation phi. So we'll get a approximation phi to S over R. Now, how do we get from an approximation? So we'll essentially get a t-bit approximation to S over R, or rather a little bit lower than t, but we'll get an approximate answer to S over R. But then we need this denominator R over here. So how do we get there? And that's the idea of the continued fraction. So the first thing is that we have to choose. So let's take n, which is our domain of the numbers that we'll be choosing from. And let n be is equal to 2 to the power L, right? And we can just take this maybe an inequality. And we take t to be equal to 2L plus 1 plus log of 2 plus 1 over 2 epsilon. Just like in the phase estimation algorithm. So basically what we get is a 2L plus 1 bit approximation of, so phi is a 2L plus 1 bit approximation of S over R. That means that we have phi minus S over R is less than 1 over 2 to the power 2L plus 1. And we also have 2L less than N less than R. Okay, so that's the order finding algorithm. And now to go to continued fractions, so there we'll need a theorem. So the theorem states the following. So on to continued fractions now. Last time we had seen how a rational number can be represented as a continual fraction, and we saw that the continued fraction algorithm was also efficient. So the theorem is the following, and this is the key theorem that will be needing to use the continuous fraction. So theorem is the following. If S over R is rational such that GCD of SR is equal to 1. So there is no common factors. And there exists a phi such that S over R minus phi is less than 1 over 2R square. Suppose such a phi exists, then S over R is a convergent of the continued fraction of phi. Right. So suppose such a phi exists, and such that the difference between S over R and phi is less than 1 over 2R square, then S over R is a convergent from the continued fractions. So we get this phi from our algorithm, order finding algorithm. And so all we need to do is this condition apply, right? So let's check that. So we know that phi is a 2L plus 1 bit approximation, right? So S over R minus phi is less than 1 over 2 to the 2L plus 1, right? This we know because we have chosen T to be 2L plus 1 plus log 2 plus 1 over 2 epsilon. So we can approximate phi S over R by phi to within 1 over 2 to the power 2L plus 1. But we also have this inequality, right? R is less than 2 to the power L, which is less than or equal to N. So substituting that inequality over here, right? We have R is less than or equal to 2L. And therefore, from here, we get less than 1 over 2 to the R square. So therefore, in our case, this inequality holds, and we can use the so once at the end of our order finding algorithm, we'll get this approximation, and we can use the continued fraction of phi to find the fraction S over R, and from there we can get. There are a few more details over here, which I'm ignoring, but that's the approximate idea. Now, the only problem that can occur is that in our S over R, it may happen that S and R have a common factor. In which case, suppose S and R have a common factor, then instead of getting S over R, we'll get S prime over R prime with GCD of S prime R prime is equal to 1. That's because the continued fraction algorithm always returns the fraction with in the lowest terms, right? But instead of S over R, we'll get S prime over R prime, where R prime is some multiple of R. So in this case, the adjustment we have to do is that we have to run the algorithm again. So run the order finding algorithm again. And then we'll get maybe S double prime or R double prime. And then one can show that with sufficient probability, with positive probability, I can say, we have GCD of S prime S double prime is equal to 1. That happens with high. One can show that this happens with a positive probability. And then we can extract R because both of these represent the same fraction, right? This is equal to S prime over R prime, both of them, but maybe it's just some common factor which is there. If S prime and S double prime don't have a common factor, then we can extract R as LCM of R prime and R double prime. And that's about it, right? And so once we do the order finding algorithm, we'll get some approximation to S over R. We'll run that through the continued fraction algorithm to get a fraction S over R, which is in terms of the lowest common denominator. And mostly will be done over here. But in case that S and R have a common factor, then we have to run the algorithm again, and then we compute the LCM of R prime and R double prime to get our unknown period R. So that's about the order finding algorithm. And in the next video, we'll see how the order finding can be used for factoring. What is the connection between order finding and factoring?